Get ready for an astronomical revelation. After years of speculation and meticulous research, the scientific community is buzzing with excitement as they announce a groundbreaking discovery, the first ever white hole. But what exactly is a white hole, and why has it stirred such a frenzy among astronomers? How does this remarkable finding impact us as individuals? Join us as we delve into this cosmic breakthrough, unraveling the mysteries of the white hole and exploring its significance in the grand tapestry of the universe. Stay tuned for an enlightening journey into one of the most intriguing discoveries in space exploration. You're likely familiar with black holes, those massive, deep space entities that devour anything in their vicinity. Their counterparts, white holes, are equally intriguing, yet operate in the opposite manner. To grasp the concept of a white hole, let's start by understanding black holes. Remember, many attributes of black holes are mirrored in white holes, but in reverse. Black holes vary in size and are categorized into three primary types based on their mass and size. The smallest are primordial black holes, hypothesized to be as tiny as an atom, but with the mass of a large mountain. The most common type, stellar black holes, can possess a mass up to 20 times that of the Sun, yet are compact enough to fit within a 10-mile diameter sphere. Their intense gravitational pull stems from this concentrated mass. Within our Milky Way galaxy, it's estimated that there are numerous stellar mass black holes. The largest category, known as supermassive black holes, outweighs 1 million suns combined and could be contained within a sphere the size of our solar system. It's believed that every large galaxy harbors a supermassive black hole at its core. Our galaxy's central supermassive black hole, Sagittarius A, has a mass equivalent to about 4 million suns and could fit inside a volume comparable to the size of our Sun. But how do black holes originate? Primordial black holes are theorized to have emerged shortly after the Big Bang in the universe's nascent stages. Stellar black holes are born from the gravitational collapse of the core of a massive star. This implosion often triggers a supernova, a stellar explosion that ejects part of the star into the cosmos. Scientists believe supermassive black holes were formed around the same time as their respective galaxies, with their size correlating to the galaxy's size and mass. Although invisible due to their intense gravity, which traps even light, the presence of a black hole can be inferred from its gravitational effects on nearby stars and gases. For instance, the motion of stars orbiting an unseen point in space might indicate a black hole's presence. When a black hole and a star are close, the intense gravitational pull can strip gases from the star, forming an accretion disk around the black hole. As gas spirals into the black hole, it heats up and emits X-ray light, detectable by NASA's telescopes. These observations help astronomers learn more about black holes. As for our Sun, it lacks the necessary mass to transform into a black hole. At the end of its life, after becoming a red giant and depleting its fuel, the Sun will shed its outer layers, leaving behind a glowing ring of gas known as a planetary nebula. In the distant future, our Sun will ultimately transform into a cooling white dwarf star. This long-term cosmic event need not concern us now. Meanwhile, in the realm of cosmic phenomena, white holes present a fascinating contrast to black holes. Essentially, a white hole is the theoretical reverse of a black hole. While material is irretrievably pulled into a black hole's event horizon, a white hole is thought to forcibly expel material and light from its event horizon. Attempting to enter a white hole would be a futile and perilous endeavor. The intense gamma radiation it emits could annihilate any spacecraft and its crew. Furthermore, the structure of space-time around a white hole increases the required energy for entry exponentially as one approaches it. In essence, penetrating a white hole would demand more energy than the total available in the universe, making such an attempt practically impossible. The theory of white holes originated from the intense interest in black holes, spurred by Albert Einstein's groundbreaking work in 1905. Einstein discovered that time perception varies for accelerating observers, but remains constant for those moving at a steady pace or stationary. He also found that the speed of light is independent of motion. His subsequent theory of general relativity proposed that gravity is not a physical force, but a distortion of time and space caused by objects with mass. Building on Einstein's work, Carl Schwarzschild used Einstein's field equations to derive an equation for mass in a region of space entirely devoid of matter. This led to the Schwarzschild metric, a complex mathematical model that describes a black hole. Schwarzschild's model depicted a static black hole, one without any electric charge or rotational movement and unchanging in size, essentially a timeless black hole in space. This mathematical representation laid the foundation for understanding black holes and influenced the theoretical development of white holes. The concept of event horizons in black holes is such that, to an external observer, all events within or beyond this horizon seem to occur in an infinitely distant future, essentially rendering these events non-existent. The Schwarzschild metric illustrates that in these idealized black holes, space and time interchange roles. Here, the singularity of a black hole represents an inevitable point in time, not a location. When we reverse time in the context of a real black hole, we observe a collapsing star. Conversely, reversing time in the context of an eternal black hole theoretically leads to the concept of a white hole. The existence of white holes, however, remains a topic of debate among scientists. Although white holes comply with the principles of general relativity and are mathematically valid, their practical existence is questioned. Some researchers label white holes as an impossible possibility, acknowledging their theoretical basis while doubting their observational reality. This skepticism is partly based on the second law of thermodynamics, which states that entropy in the universe must remain constant or increase. White holes, in their theoretical construct, seem to contravene this law, further fueling the debate about their existence. Entropy, often associated with chaos, is more accurately defined as an increase in the number of possible states for particles within a system. For instance, a demolished house, now rubble, represents higher entropy, as it can be rearranged into various structures, unlike the single state of a fully built house. While local decreases in entropy are possible, the overall entropy of the universe must increase. Black holes exemplify this by consuming low-entropy matter, like planets, and dispersing it, thus increasing the chaos in space. On the other hand, white holes, which are theorized to eject matter, seemingly violate this principle by reducing overall entropy. This apparent contradiction leads to debates among physicists about the nature of time and its direction. However, it doesn't conclusively disprove white holes' existence. Theoretical physicist Carlo Rovelli proposes that when black holes cease to evaporate and shrink, they undergo a quantum bounce due to space-time constraints, transforming into white holes. This suggests that black holes become white holes almost immediately upon formation. However, due to gravity's time dilation, they continue to appear as black holes to outside observers for billions of years. Following this theory, black holes formed early in the universe's history could be on the brink of transitioning into white holes, potentially bursting into cosmic rays or other forms of radiation. This hypothesis might have been observed in 2006, when NASA's SWIFT satellite detected an unusual gamma-ray burst, GRB 060614, in a peculiar region of the sky. Lasting 102 seconds without being linked to a supernova, GRB 060614 didn't fit the typical profile of gamma-ray bursts, which usually last between 2 and 30 seconds and are often associated with star explosions. This anomaly hints at the possible existence of white holes, challenging our understanding of cosmic phenomena. The mysterious gamma-ray burst GRB 060614, detected in a galaxy with scarcely any stars capable of creating such explosive events, left astronomers and astrophysicists scratching their heads. This burst seemed to emerge out of nowhere, only to vanish just as quickly, defying typical astronomical explanations. This peculiarity led scientists years later to propose a groundbreaking hypothesis. Could GRB 060614 have been a white hole? This hypothesis gains strength because the characteristics of GRB 060614 align precisely with what one might expect from a white hole. A sudden, intense eruption of matter and energy from a seemingly imperceptible origin, vanishing almost as quickly as it appeared. The intrigue deepens as this theory stands unchallenged by current scientific models, leaving us to ponder the enigmatic nature of white holes. What are your thoughts on the possibility of white holes? Drop your ideas and theories in the comments below, and let's explore this cosmic mystery together.